Here I'll describe a simple momentum balance for waves. We'll start with a well-known F equals ma. And notice I've got an arrow over the F and an arrow over the A because they're vectors. In oceanography, we usually rearrange this as A equals F over m, where F over m is the force per unit mass. In this form, we have the acceleration, which is the response, on the left side of the equation, and on the right side of the equation, we have the force. Acceleration is the change in velocity with respect to time. We can rewrite this vector equation in terms of its components. So we have du dt, I hat, where u is the component velocity in the x direction, and I hat is the unit vector in the x direction, plus dv dt, j hat, where v and j are in the y direction, plus dw dt, k hat, where w and k are in the vertical direction, equals 1 over mass times the quantity fx, I hat, plus fy, j hat, plus fz, k hat. And fx, fy, and fz are in the components of the force in the x, y, and z directions. That's a full vector equation. We can look at one component of this vector equation separately and then put it back together. So let's look at the terms that are in the x direction. We have du dt equals fx divided by m. That's the force per unit mass in the x direction. Now I need to specify a force. In this case, I'm going to use the pressure gradient force. First, I'm just going to say this equals PGF, an abbreviation for pressure gradient force. And that's the force per unit mass. And really, it's the pressure gradient force in the x direction. That can be written as negative 1 over rho naught, where rho naught's the reference density, dp dx. The negative sign is there because the pressure gradient force acts to accelerate water from high to low pressure. So if pressure is increasing in the positive x direction, the pressure gradient force is acting to accelerate water in the opposite direction, and that'd be a negative acceleration. Now, if you've watched the videos for hydrostatic balance and horizontal pressure gradients, you know that we can write dp dx in a different way if we use that hydrostatic balance as well. I'm going to write my conditions I'm going to write the assumptions I'm making. I'm going to assume hydrostatic balance. That way I can rewrite dp dx in terms of its contributions. And I'll assume homogeneity. That's another way of saying constant density. And I'll also assume constant atmospheric pressure. If you look back at the horizontal pressure gradients written in terms of information from the hydrostatic balance, you'll see that there are 3 terms. One from atmospheric pressure gradient, one associated with sea level gradients, the barotropic part, and the last from density variations, and that's the baroclinic part. I've gotten rid of the density variations by assuming homogeneous or constant density, and I'm also assuming there's no atmospheric pressure gradients. That leaves us just with the term that depends on the sea level gradients. In that case, dp dx equals positive g times rho naught times d eta dx, how sea level changes in the x direction. It's important to remember this is an expression for the pressure gradient, not the pressure gradient force. I have to multiply by negative 1 over rho naught. Under these assumptions, the balance acceleration equals pressure gradient force is du dt equals negative g times d eta dx. This is a balance that works reasonably well for surface gravity waves and also for tides. Now let's consider a progressive sinusoidal wave. Here's an equation for the surface elevation we've seen before. Eta equals eta naught, where eta naught is the amplitude, times sine, and inside the sine is the argument kx minus omega t, where k is the wave number, and we could write that. K equals 2 pi over the wavelength L. And the wave frequency omega is 2 pi over the period capital T. I can take the partial derivative of eta with respect to x to get d eta dx. And for that, I can treat that time part as constant. In this case, d eta dx is eta naught times cosine kx minus omega t. I have to apply the chain rule and take the derivative with respect to x of kx minus omega t. That's just k. And I'll squeeze that in out in front. Now we can write du dt. I'm running out of room, so I'm going to erase some of the equations up top and start working up there. I want to figure out what u is. I know what du dt is. To get u, I'm going to have to integrate that equation. And I'm going to have to integrate it with respect to time. And we could go and do that, but I'm going to take a guess first, because I know that the derivative of sine is cosine. So I'm going to just guess something reasonably close. I'll write u as u equals u naught sine kx minus omega t. The time derivative of this expression is u naught times cosine kx minus omega t. And then I have to apply the chain rule and take the derivative of kx minus omega t with respect to time. And that's negative omega. And I'll put that over there. From the balance below, we're saying this all equals negative g k eta naught cosine kx minus omega t. We have the same cosine term on both sides. So if we're equating them, those would cancel out. We also have a negative sign on both sides. So those would cancel out. For this to be true, u naught omega has to equal gk eta naught. So u naught, for this to be true, has to equal eta naught times g times k divided by omega. If you remember, the wave phase speed c equals wavelength L over period t. Also equals omega over k. In this equation, we have k over omega, which is 1 over c. For a shallow water wave, the wave phase speed E equals square root of GH, where H is the water depth. In that case, we could substitute in the C. But before we do that, let's rewrite the more general equation here as eta naught GC divided by C squared. I'm doing that because I know where I want to get to. So for the shallow water wave, if we substitute in square root of GH, I'll just substitute it in for the C squared. So we have eta naught times G times C divided by G times H. And the G's cancel out. And we can write eta naught over H times C. Now C is the phase speed, and eta naught over H is the ratio of the wave amplitude and water depth. What this says is, usually the currents associated with waves are much smaller than the wave phase speed. They're much smaller than wave phase speed usually because eta over H is much less than 1 in many, many circumstances. It's only this circled part that is specific to shallow water waves. Everything else is more general. So we have a solution for eta and u that are consistent with this balance. And the balance was acceleration equals the pressure gradient force.